Good morning. So I'm Glenn Vanderburg. I'm the Director of Architecture at LivingSocial. But I'm not actually here to talk to you about architecture per se. I'm here to talk about, as Neil said, something that kind of underlies that and everything we do, which is software development as an engineering discipline. And there are really two prevailing schools of thought or views about what that looks like, what software as an engineering discipline looks like. And the first one is it enjoyed a fairly long heyday in both academia and industry for about 30 years, starting in 1969 at the second NATO Software Engineering Conference in Rome. And this view is that software must become like engineering. It must become mathematical and defined, document and model driven, analytical and verifiable. More recently, another view has taken hold, and over the past 10 or 15 years, and it's best expressed by this tweet I saw a little while ago. I've hidden the name of the person involved. Let's stop calling programmers engineers. It's factually wrong and insulting to both professions. Same goes for software architects. In other words, the view is that software development is incompatible with engineering, that software development is more like an art, or it's more like a craft or a science, or maybe it's more like gardening or movie making, or it's a special snowflake thing that is unique and unlike anything that's come before. But whatever it is, it's not engineering. I'm here to tell you that both of these views are wrong. And they're wrong because they're rooted in some fairly deep misconceptions, and they're rooted, at least partially, in the same misconception. The first view, which is, we should become like software engineering with big capital letters, has two big misunderstandings at its base. The people involved in that movement and that school of thought misunderstood software, and they misunderstood engineering. Which, is kind of unfortunate. The people who hold the second view, which is that software development is not engineering, they've shed the first misconception, I think. They understand software development and what it's like pretty well. But they still misunderstand engineering. And they still misunderstand it in exactly the same way. Essentially, people who hold the second view, tried it the old way or looked at it the old way and said, okay, well, if that's what software engineering has to be, because that's what engineering is like, then that's not going to work. And so we don't think software can be engineering. The curious result of this, situation is that we work in a field where the term engineering refers to practices that everybody knows don't work. And this is curious because in every other engineering field, the word engineering is reserved for practices that work, right? And so, the past couple of weeks I saw this tweet. My software engineering education was valuable in part because of the deep understanding it gave me of bad methods. I sympathize with that view, but I don't like the situation where that is the impression we get. So if classical software engineering doesn't work, what does work? Well, I think at a software architecture conference in 2015, we can probably all agree on some things about how to build software that works and a process that works to do it reasonably reliably. We still don't have all the answers, but we've learned that the best way to build software is to be iterative and incremental and empirical, which means, test-driven or test-validated, oriented around tests and QA, that kind of validation of things, rather than analytical, and experimental. And if you are like most of our field, and if you're like most of society, frankly, that holds some common misconceptions about engineering, you look at this list and you're saying to yourself, that doesn't sound much like engineering. But like I said, while we understand software pretty well, we still misunderstand engineering. If you think engineering is necessarily planned, analytical, mathematical, and predictable, then of course, from our experience in the software field, software development is incompatible with that. And many people do think that. And as I said, it's mostly wrong, because there are actually a lot of engineering disciplines. And you know what they have in common? Well, mostly that they're called engineering. They're really different from each other. Some are closer than others, and it's a curious fact that classical software engineering was mostly modeled, as near as I can tell, around the engineering disciplines that are least like software development, which is civil and structural engineering. When I started doing the research that ultimately led to this talk, I noticed a curious thing. It's really hard to find a definition of engineering written by engineers. It's easy to find a definition of civil engineering and structural engineering and chemical engineering and any particular engineering discipline you want. But it's hard to find a general definition of engineering independent of a particular branch. And in fact, engineers rarely write about engineering. In a book called Discussion of the Method by a mechanical engineering professor named Billy Vaughn Cohen at the University of Texas, he wrote this: "Unlike the extensive analysis of the scientific method, little significant research to date has sought the philosophical foundations of engineering. Library shelves groan under the weight of books by the most scholarly, most respected people analyzing the human activity called science. No equivalent body of research treats the engineering method." And he's exactly right. These are all the books I've been able to find about engineering qua engineering, without being about a particular engineering discipline. And I'm going to quote from several of these. But it made me think, over the past 45 years in the software field, we've spent a whole lot of time arguing about what engineering is and whether programming qualifies as engineering. And if we've done that, then why isn't there more engineering literature about the nature of engineering? And the answer seems to be, and this is one way that software development really is unlike every other engineering discipline. As near as I can tell, we're the only one that's had a big existential crisis about whether we're engineers or not. The rest of them just get down to business and start engineering. The attitude seems to be that, well, look, we're building and defining a disciplined way of creating certain kinds of useful artifacts for people. Therefore, it's engineering. What else could it possibly be? Right. So, fortuitously, in the past week, the terrific consultant John Cook tweeted this: "Arguing about whether software development is art or engineering is like arguing whether light is a wave or a particle." I didn't ask him whether he was prompted to say this by seeing that I was giving this talk or anything. But given my interests, I responded to him, and I liked his response to me even better. It is like engineering sometimes, just as light is like a particle sometimes. But light isn't a wave or a particle, it's light. And that's an important point. Yes, software development is like an art, and it is like a science, and it is like a craft, and it is kind of a unique thing that's never existed before. That doesn't mean it's not also engineering. And we should think of it that way. So, let me get down to the business of disabusing you of your misconceptions about engineering. What most people think engineering is: straightforward and predictable, constrained by physical laws and forces, done via documents, applied science, and finally, mathematical and analytical. I'm going to address each of these in turn, and I'm going to spend quite a bit of time on the mathematical one today. So let's go. Engineering is straightforward, well-defined, and predictable. You can see that in this quote by Bruce Eckel. Now, a few years ago, he wrote, "Programming is not some kind of engineering where all we have to do is put something in one end and turn the crank." Now, Bruce Eckel is a really smart guy, and I don't think, if you were to corner him and ask him about it, he would really agree with this. It was a throwaway sentence on the way to a larger point, but he wrote it, so I get to make fun of it. Let's be clear. There is no kind of engineering where all you have to do is put something in one end and turn the crank. Engineering, even civil and structural engineering, is a creative task that is full of false starts and dead ends and backtracking and experimentation and things like that. Eugene Ferguson, in his book Engineering and the Mind's Eye, writes, the conversion of an idea to an artifact, which engages both the designer and the maker, is a complex and subtle process that will always be far closer to art than to science. And I've already mentioned Billy Von Cohen in his book. He wrote, the engineering method is the use of heuristics to cause the best change in a poorly understood or uncertain situation within the available resources. Does that sound like software development or not? The only thing he left out is that the situation is changing under our feet, too. But if you read on, he says that's true of other engineering disciplines as well. Second thing that people think engineering is like. Engineering deals with physical materials and is constrained by physical forces. And, software, on the other hand, is not dealing with physical materials. We work with information and abstraction, and we're not constrained by the vagaries of physical materials or physical forces aren't primary. We're not constrained by 3 dimensions. Okay. I'll grant this point. Of course, all prior engineering branches have dealt with atoms, not bits. But here's the thing. That's not because there's some rule that engineering has to deal with physical materials and physical forces. It's because nobody's ever had the opportunity to build useful things out of pure thought stuff before. And we do. We do have constraints that we labor under. And I mentioned that other engineering disciplines are all different from each other, and they have different forces they deal with and different constraints. And we do too. We're constrained by our machines and their characteristics and the materials they're made of indirectly. I read an article recently where Grace Hopper, when she was teaching programming, used to give her students a length of wire that was the farthest distance electricity could travel in a nanosecond. And, when our computers are this size, maybe we don't care about that so much. But when your computer's the size of a room, knowing that electricity can only travel this far in a nanosecond is kind of important. We're constrained by light and electricity. We're constrained by rules of logic. And we're constrained by laws of complexity. And those laws of complexity help determine how fast certain algorithms and ways of solving a problem can run. They determine to some degree what problems are reasonably solvable by programming, and they constrain what kinds of designs and architectures can be understood and maintained over a long period of time. Third thing, people think engineers produce drawings and documents. In 2007, I got to see David Parnas, who is one of the towering figures of software engineering and made many important contributions. But I don't agree with everything he said. And I heard him say this: in engineering, people design through documentation. And that's true, but, the documentation isn't the central thing. It's not quite as important as he was trying to imply. Here's another quote from Eugene Ferguson in Engineering in the Mind's Eye. Although the drawings appear to be exact and unequivocal, their precision conceals many informal choices, inarticulate judgments, acts of intuition, and assumptions about the way the world works. I'll talk more about documents later. Fourth misconception: engineering is applied science. In his book, The Design of Design, Fred Brooks, whom most of you probably know as the author of The Mythical Man Month, wrote about his experiences as an undergraduate engineering student at Harvard in the 1950s. And he wrote about the then new head of engineering at Harvard, the Nobel Prize-winning physicist John Van Vleck. And Brooks wrote, Van Vleck was very concerned that the practice of engineering be put on a firmer scientific basis. He led a vigorous shift of American engineering education away from design toward applied science. The pendulum swung too far, reaction set in, and the teaching of design has been contentious ever since. In an address to the Royal Aeronautical Society in 1923, aeronautical engineer J.D. North said, airplanes are not designed by science, but by art, in spite of some pretense and humbug to the contrary. There is a big gap between scientific research and the engineering product, which has to be bridged by the art of the engineer. Walter Vincenti, in What Engineers Know and How They Know It, another great book, said, engineers frequently have to make decisions of great practical consequence in the face of incomplete and uncertain knowledge. Does that sound like software development? Of course it does. And finally, back to Billy Vaughan Cohen again. The thesis that engineering is applied science fails because scientific knowledge has not always been available and is not always available now, and because even if available, it is not always appropriate for use. We'll see some examples of this later as well. And finally, the fifth big misconception people have about engineering. Engineers prove their designs with mathematics. This takes a little bit to dig into, so we'll spend some time here. Another quote from Eugene Ferguson. Structural analyses, and indeed any engineering calculations, must be employed with caution and judgment because mathematical models are always less complex than actual structures, processes, or machines. So what that tells us is that the math doesn't prove the design's correct. It's one of those heuristics that Billy Vaughan Cohen was talking about in the engineering method. Hold that in your mind, and we'll see how this works. As a father, I've tried to model myself and emulate the father in Calvin and Hobbes. And one of my favorite cartoons with Calvin and his dad is this one. Family's on vacation, driving over a bridge, sees a sign. How do they know the load limit on bridges, Dad? And just as I would if I were in that place, Dad says, well, they drive bigger and bigger trucks over the bridge until it breaks. Then they weigh the last truck and rebuild the bridge. And Calvin goes, oh, that makes sense. And, Mom reacts just the way my wife does. And so why is this funny? It's funny because it's absurd, right? Nobody would ever do that. How many of you have seen the video of the Boeing engineers winching up the wings of a 777 until they break? They put a 777 prototype in a hangar and hooked the wingtips up with cables to winches on the ceiling of this hangar and started cranking them up. And they crank them up until the wings break, explosively and catastrophically, as you might imagine. And if you watch the video, and I encourage you to seek it out, it's easy to Google for and find, when the wings break, the engineers get all excited. And it's not just because we like to see stuff break, right? It's because they broke at the predicted stress and angle. What does that mean? It means that the experiment proved the math. It proved their model was correct, but they didn't know for sure until they did the test. And it turns out, if you study the history of engineering, that mathematical modeling and formalisms and formal methods were introduced to the field of engineering not primarily as a tool for correctness and robustness, although they help with that a lot. They were introduced as a cost-saving measure. In the other engineering disciplines, the primary cost is the cost of materials and building. And if you can save yourself from having to build prototypes and test them, or build as many prototypes and test them, you save money. And if you have a good mathematical model, you can help yourself do that. And also, in the absence of, well, even with a mathematical model, you have to over-engineer to give yourself a safety margin. But the better your mathematical model is, the less you have to over-engineer, and that saves money on materials. Ask your friendly neighborhood aeronautical engineer how much math he would do if creating a prototype and doing a wind tunnel test or whatever were instantaneous and free. The answer is probably not none, but it's a lot less than they do because building models and doing wind tunnel tests are expensive. I've told before in other previous adaptations of this talk, I've talked about the bridges of early 20th century Swiss engineer Robert Maillard, and he designed these beautiful, graceful bridges that were very cheap because they were light on materials. They were making novel use of this new material called reinforced concrete and everything, and he did not have math sophisticated enough to model these bridges. But he tested them, he had an intuitive understanding of the physics, and even though he was criticized for being a charlatan because he didn't have the math and therefore his bridges would fall down someday, except for the one that was destroyed in an avalanche, they're all still standing. Sorry. Glad I caught that one. His contemporary, Leon Moissef, developed the most advanced mathematical and analytical model of suspension bridges ever. And to show off what it could do, he used it to build the Tacoma Narrows Bridge, which fell down in a light wind. Because his model turned out to be incomplete because it didn't account for forces that they'd never actually measured before in suspension bridges. I want to show you another example of that kind of empirical engineering. A couple more examples. The Gateway Arch in St. Louis is described by that equation. That's a little oversimplified, but basically that's the equation. The interesting thing is that the form of that arch, the shape of it, could have been determined with really strong precision, even if we didn't know that equation, because it's the shape of a common household item. No, wait, not that one. This one. It's a hanging chain, or actually an inverted hanging chain. A hanging chain falls into a shape called a catenary. It's not quite a parabola. It's a little different. And engineers have known for a long time as a heuristic that if you take a catenary and invert that shape, it makes a pretty good shape for an arch. In 1671, the great Renaissance mathematician and scientist Robert Hooke articulated the physical principles behind this about even distribution of stresses and forces, and thereby elevated it from a heuristic to a principle. But the equation I showed you that describes a catenary wasn't discovered until 20 years later, in 1691. So I'm going to show you an application of this. Last year I got to check off a bucket list item. I was able to travel to Barcelona and spend a day at the enormous great cathedral Sagrada Familia by the great Catalan architect Antoni Gaudí. And I'm not the greatest photographer in the world. You shouldn't be surprised by that because that would be an amazing coincidence. But I'm going to show you some of my pictures anyway because it really illustrates these points. And I'm indebted to Jez Humble for telling me to go to the museum in the basement of this thing and see this. You can see that the towers of Sagrada Familia have a very unusual shape. And the interior is novel structurally as well. Like most great cathedrals, it has soaring, high vaulted spaces. But unlike the great Gothic cathedrals, where the apexes of the vaults had to be heavy keystones, the vaults in Sagrada Familia have at their apex skylights. And there are other interesting features, like the primary columns that go straight up until, pretty high, and then serve as a branching out point for these asymmetrical clusters of other columns that go up from there and hold up the vaults. And you're standing there in the middle of this, looking up at this ceiling of stone, thinking, I sure hope he got all this right. And, when it's finished in, they think roughly 20 years, the highest, most massive tower will be built on top of the ceiling over the highest and most open part of the church. So you really hope he got it right. Well, he did the design work on this cathedral between 1883 and his death in 1926. And he did not have, just like Robert Maillard, he did not have mathematical tools sophisticated enough to really model these structures. The architects who are currently managing the project have done a lot of computer modeling, and they've found out that the design holds up. So how did he do such a complex and novel design and know that it was right without math? Well, he exploited the catenary principle. In the museum in the basement of Sagrada Familia, you can find this model. It is an inverted string model of a different church that Gaudí built as a study for Sagrada Familia. And he built this model out of string and used little bags of lead shot to simulate uniform, intensified, force of gravity. I'm no structural engineer, so I'm sure somebody could say it better than that. But he used this to help him understand what shapes the supporting columns should be to achieve the shape of the church that he wanted. And then they cut muslin, cloth, and laid it in so they could, not be distracted by all the strings and open spaces and see the shape of the church. And then, this is pretty amazing. Get this. They took a picture of that, and they turned it upside down. So that, they could see what it looked like. And they had places where they could insert a camera and take a picture of the interior and see what the interior looked like. Now, as far as I know, they never did a full-scale model like that of Sagrada Familia, but they did partial models showing the vault structure. And some of those still exist. And the result is magnificent. You can see here is another view of how the apexes of the vaults are skylights. It's impossible from within the church, at least with my camera equipment, to get a really good picture that shows the overall structure of the interior vaults. But fortunately, there's a large model in the basement, and this is kind of what they look like. And one of his goals in designing this was that it should reflect the beauty of the natural world. And inside the church, it should feel like you're in a dense, tall forest. He achieves that effect admirably. And all of this was done with very limited use of mathematics and formal methods. It's worth going to see. So, okay, I've spent a while explaining that the popular stereotyped view of engineering is wrong. So, if you have a proper understanding of engineering and you apply it to software, what does that look like? What is real software engineering? My favorite definition of an engineering discipline is a definition of structural engineering from the Structural Engineers Association. And I want to call your attention to a few parts of it in particular. Structural engineering is the science and art of designing and making both with economy and elegance structures so that they can safely resist the forces to which they may be subjected. Note that it doesn't say anything about how to do all of this, particular methods. I propose this definition for software engineering. Software engineering is the science and art of designing and making, with economy and elegance, systems so that they can readily adapt to the situations to which they may be subjected. Since we just mentioned economy, I want to talk a little bit about the economics of software development. And a lot of this comes from a man named Jack Reeves and a great paper that he wrote in the C++ Journal in 1992 called What is Software Design? Traditional software engineering was developed by an analogy with traditional engineering disciplines. And the analogy goes something like this. You have an engineer that sits and does a design on paper using documents and math. And he produces that design and he hands it off to builders who build that design into a finished structure. What's the most costly part of this process? Which stage costs the most money? The third one, right? Construction. You have to buy materials, you have to pay laborers and all that stuff. And so the analogy went, okay, for software development, we'll have engineers sit down and design the system on paper and produce a document which they hand to laborers who turn it into a finished artifact. But this really didn't work very well, and in particular, that second stage, we never really found a good way for the engineer or architect to describe the system in sufficient detail that the laborers in their cubicles, could faithfully reproduce it and produce a working system. And the result was that those laborers had to, A, curse the software engineers a lot, and B, do a bunch of redesign while they were building the system. And so, some people said, hey, if we end up doing a bunch of redesign, if the laborers in the cubicles, the coders, if they end up doing a bunch of redesign anyway, wouldn't it work better if we had them move over and be the software engineers? And you know what? There's another thing wrong with this analogy. Customers aren't paying for files of ASCII source code. That's not the artifact we're delivering them. We're delivering working software to them, packaged and deployed and whatever. That's actually the design. And you know what? It's a document. Amazing. Well, if writing the code is the design and engineering part of it, well, not all the engineering part of it, but if that's the design, and the code expresses the design and is our document, who are the laborers? Compilers, programming language implementations that take that design document, the source code, and turn it into a finished artifact that we can deliver to customers. What's the most expensive part of the bottom row? The first one, producing that document. And this is an important point. The economics of software engineering are very different from that of structural engineering. They're actually not all that different from the economics of electrical engineering and chemical engineering, but they're very different from civil and structural engineering. Because in most traditional engineering disciplines, the most expensive part by far is actually building the thing. And that's the cheapest part for us. It's nearly instantaneous, and it's essentially free. So if economy is our goal, shouldn't we take advantage of that? And that's why good software engineering is iterative and incremental. We build these documents, and we build them, and we test them, because doing that is cheap. And in fact, given our current understanding of software development, that may change someday, but right now, validating it through building a prototype, that is, compiling the thing, and testing that prototype is much less expensive than doing a lot of formal validation. Much less expensive. So we should be biased that way. David Parnas, who said, engineers design using documents, proposed a specification notation that he called tabular mathematical expressions. And here's an example. I don't know how to explain that. So I produced a grossly simplified, and this is so simplified as to be a caricature, right? Don't judge tabular mathematical expressions by this alone. But I'm making a point about the costs of certain ways of doing things, and where our documents are and where our models are and where our math is. So here's a grotesquely oversimplified version of a tabular mathematical expression that is used as a specification notation for how a certain part of a software system should work. Do you see the error in it, by the way? Too late. So here are some different documents that express the very same thing. This one's test unit. This one's RSpec. This one's Cucumber. This one's a fit fixture. All of these are documents that encode the same specification as the tabular mathematical expression. They're also executable. They're documents, but they're not mere documents. They're documents that do useful work for us, of validating the design that we've produced for this specification. See, our tool, our material, our stock in trade is code. It's a document. It doesn't have to be, and it shouldn't be, our only document about how our software works. Architectural diagrams and design documents and things like that are useful. But that doesn't mean the source code isn't a document. It's a document. It's mathematical. It's formal. It's verifiable. That's where our model is. It's in the code. Final thing. This is a diagram of the process elements of extreme programming taken from Kent Beck's original extreme programming book. And in that book, he has a chapter that basically says, he's answering a lot of objections to people. And he says things like, simple design can't possibly work. And he says, well, yeah, you're right, except it's buttressed by these other practices that backfill and compensate for its weaknesses. And this is a diagram of those interrelationships that he describes. And a friend of mine, a number of years ago, pointed out that we would look at this diagram of a software system and say, that's really tightly coupled. Why do we think that's good? And I started thinking about that, and I thought, well, it actually seems good to me. It seems to reflect reality to me. It matches up with this Billy Vaughn quote, which says, engineers cannot simply work their way down, Billy Vaughn Cohen, engineers cannot simply work their way down a list of steps, but must circulate freely within the proposed plan, iterating, backtracking, and skipping stages almost at random. So waterfall doesn't work in traditional engineering methods either. And so I thought maybe that diagram of interdependencies, that was an accidental view of the system and not the essence of what an agile process is like. And I started looking at those dependencies and trying to sort them in different ways and group them into different kinds of dependencies. And what I came up with is that you can take the core practices of extreme programming and lay them out, and they correspond quite nicely to different scales of artifacts in the system. Pair programming tends to work on the level of statements and methods, and unit testing tends to work on the level of methods and classes and interfaces, and on up to short releases. They're validating whether you got the solution right. Each of those practices is a way of getting feedback and validating your decisions at different scales of your system. And then if you look further at how XP and other agile processes practice these things, they do them on different time scales. Pair programming works, you get feedback on the level of seconds. Unit testing, you get feedback on the level of minutes. and all the way up, and short releases, you get feedback about whether you've built the right system for your client on the level of weeks or months. And you'll note that this corresponds to cost. This kind of process is an optimized, economical feedback engine. We gather feedback about decisions at different scales as rapidly as is cost effective to do so. It's much more expensive to give it to our customer and let them validate and say, oh yes, this solves our problem perfectly. So we don't do that quite as often. And there are other things down the path that try to get to that. This is not a defined process where you plan and design and then build like people's stereotypes of an engineering process. It's an empirical process, but it's no less disciplined for all that. And it's no less rigorous for all that. The reality of software engineering is that software development is engineering. It's still immature. We're still figuring it out. But there's no need to copy other engineering disciplines, because you know what? Within reason, the other engineering disciplines didn't copy each other either. We can best advance by staying true to what we know about the nature of software development and working and sharing and writing and talking about better ways to do things and better ways to engineer our software. Thank you very much.